All right. So what did you get for the horizontal asymptote?
2.
Horizontal asymptote is that y equals 2. Good. I feel like on one of our chapter tests they did this where they put like x equals 2. So just be careful that you're aware that it's y equals 2 for the horizontal asymptotes and x equals 2 for vertical asymptotes. Just because if they put both and you don't see the y equals 2, you might just circle the first one you see that says 2. I think one of the students did, and she got all mad at herself because she was like, I didn't even read it. So just be careful. No, actually it wasn't. It was somebody in 6th period. All right, for vertical asymptotes, you got to factor the top and bottom. So what is the top factor to? 2x plus 3 and what? X minus 4. And then what is the bottom factor to? Okay, good. So what's the vertical asymptote? Sorry. What's the vertical asymptote? 8. Just x equals 8. Y equals 2, x equals 8. Who can tell me why x equals 4 is not a vertical asymptote? Good. It's a hole. Good. It is a removable discontinuity. All right. Why don't you guys try, for number 1, let's just talk about it, obviously, because you don't have to write that out. But explain how horizontal and vertical asymptotes are related to infinity. So how would you be able to figure out a horizontal asymptote? How is that related to infinity? Good. So when the limit is being taken at infinity, what is the limit as x goes to infinity or negative infinity? And what is a vertical asymptote? How does that relate to infinity? Good. So for the horizontal asymptote, it's when the limit is approaching infinity. So like as x goes to infinity, we're taking the limit at infinity. So what is the limit of x equals infinity or whatever? A vertical asymptote is that the limit equals infinity. So the limit of da-da-da-da-da equals infinity, meaning it's going up or it's going down. So that's how those two are related to that. Number 2, if m is an even function with vertical asymptote x equals 2, and the limit is x approaches infinity of m of x equals 0, draw a possible graph of m of x. Why don't you guys try that one? It doesn't have to look exactly like mine, but it has a vertical asymptote at x equals positive 2. And if it's even, it means it also has a vertical asymptote at x equals negative 2, because it just means that it's symmetrical across the axis. It says draw a possible graph. There's a lot of different ways that it could look. It has to have a limit as x approaches infinity of 0. What does that mean? A horizontal asymptote at 0. So it might look something like this. Like I said, there's a lot of possible different ways it could look, but it could look something like that. For the middle part? Absolutely, yeah. Whatever you want. This is just one possible one. This is one that I've seen before. That's why I drew it. All right, did you guys get a chance to do number 3? No. All right, try number 3 right now. What's the degree of the top on the second one? 3. What's the degree of the top on the bottom? 3. Good. 3. So it's leading coefficient because the square root of 6 would be 3. What's the leading coefficient on the top? 5. And what's the leading coefficient on the bottom? 7. Plus or minus the square root of 7. So there's 2 for that one. So it's y equals 5 over the square root of 7 and y equals 5 over the square root of negative 7.
Can you bring the square root to the top? Or does it matter?
It doesn't matter.
Let's do that. Let's try it.
Let me verify that really quick, though, because that's not what the answer has. So let me check something really quick. Set what equal to 0? Okay, so for the vertical asymptote, we can make this, we want this x squared minus a squared piece to equal 3. Is that right?
Yes. You still need the 2. Yeah.
Say it again.
But you need the 2 in front.
So, okay, let's rewind a little bit. So let's talk about what it means to have a vertical asymptote. How do you know when something has a vertical asymptote?
When the bottom equals 0.
When the bottom equals 0?
Yeah.
Okay, so we want to know when this equals 0. Zero, sorry. And then what does the 3 have to do with it? Like, where would we plug the 3 in? What equals?
The vertical asymptote, the bottom.
It's where we have a vertical asymptote at all of our x values, right? So that's where x would equal 3. So it would be 2 times 3 squared minus a squared equals 0. So you guys said, don't you need the 2? Not really, because the 2 disappears when you divide it by 0. So I have 9 minus a squared equals 0. So if I subtract 9 over to the other side, I have negative a squared equals negative 9. So yeah, a equals plus or minus 3. So a could equal negative or positive 3. For part B, that has to do with the horizontal asymptote. So if we have a horizontal asymptote at y equals 2, how would we figure that out? What is how do we figure out horizontal asymptotes again?
You take the biggest coefficients and
You take, what do you mean the biggest coefficients?
the leading.
The leading coefficient. So what's the leading coefficient of the top? B. And what's the leading coefficient of the bottom? 2. Because when I multiply that 2 into the binomial, it would be 2. So I have b over 2, and when I divide that, it should equal 2. So b equals 4. So we got a could equal plus or minus 3, and we know that b equals 4. That's definitely a possible AP Calculus question, to just testing your knowledge of the horizontal and vertical asymptotes. Don't worry about finding the point of removable discontinuity on f. That's not a big deal right now. Part 5, or question 5 I think, says draw a function g of x that satisfies all of the following properties. So why don't you guys try and draw that for me? So, if I draw my little xy axis, got something like this. So it says the domain is from negative infinity to negative 2, union negative 2 to negative infinity. What does that mean? The first one, the domain part. So what does that tell you about what it's going to look like? At negative 2, there's something missing, right? It's not even defined at negative 2. So there's no points at negative 2. It's not even defined at negative 2. So it says G has a non-removable discontinuity at x equals negative 2. So that means that it's either a jump or it's unbounded. Okay, so it's not just some point that's missing. The range of G is from negative 3 to infinity. So it starts down at negative 3 and goes up. It doesn't go anywhere below negative 3. G has one root. X equals negative 4 is its one root. So over here at x equals negative 4, there's one root right here. Remember that a root is an x-intercept. So the only one we've drawn so far is this one. The limit as x approaches negative 2 from the negative side, so this is from the left-hand side, of g of x equals 3. So the limit as it's getting towards negative 2 is up here at 3. 1, 2, 3. So that's right there. That's from this side. The limit as x approaches negative infinity, so this is a horizontal asymptote as it's going towards negative infinity, is at negative 1. So that would be everything down, let's see if, I don't know if I can make this dotted. I don't think so. So here's what I'm going to do. So a horizontal asymptote at negative 1. And then the limit, I'll make that dotted so that you guys can see that it's a horizontal asymptote. There we go. And then the limit as g of x approaches infinity is positive 1, so it has another horizontal asymptote up here at positive 1. And that's for going to positive infinity. All right, and that's pretty much all it tells us, right? Okay. So, I know that it's going this way as it goes to positive infinity. I know that it's going this way as it goes to negative infinity. So I did this one, and I did this one, and I did this one. And now we just kind of have to piece it together. So there's a lot of different ways you could draw this. I know that it definitely needs to go down to negative 3. So it needs to start at negative 3 somewhere, right? Okay. So we need to figure that piece out. So honestly, like, just probably connect the dots. Like, as long as it goes down to negative 3, you're good. So maybe it looks something like this. Like, it goes down to negative 3 and then crosses up right here and goes like that. And then maybe this piece goes like, I don't even know, like this. It's allowed to cross it, yeah. It has to follow it at some point, but it's allowed to cross it even. And then maybe we have like something that looks like this. Because it does go up to positive infinity, I know that. So it could look something like that. It's kind of a weird graph, but it works. It's not wrong. Hey, it's even exactly like the one that they drew in their solution. I'll show you what their solution was up here. Can I take this off the board? Here was what they put on theirs. Theirs is cuter than ours, but... So pretty much exactly what we drew on ours. There's a hole here, it goes to infinity up here, it goes to infinity over here, and it goes to infinity down here, and it dips down here to the point where it gets to -3. Sounds good? Alright. A new phone? No, Ricky fixed it for me because it was all cracked. So I got a nice big case for it so that I never crack it again. Ever. Well, they said that if it drops in an OtterBox, that OtterBox promises that they'll fix it for me. So if it breaks again, I have it covered this time at least. So I bought that for my husband when he had his other phone, but then he got a new phone, so he couldn't use it anymore. He loved it.
See, I dropped my phone. I was on a run and I dropped it, but that year's kind of saved it.
Did
I was
it?
like, oh, Batman saves the day.
That's awesome. Batman's the best.
Batman's awesome.
All right, there's 4 special limits we've learned about. So it says you have a number of techniques available to you to evaluate limits now, to interpret the continuity that it's dependent on those limits. Remember L'Hopital's rule? We looked at that earlier. Remember how I said sometimes they spell it differently? Anthony, I don't think you were here when we talked about L'Hopital's rule, so make sure you ask him about that at some point, because sometimes it looks like that, sometimes it looks like else apostrophe hospital, but it's a really helpful rule. So here's the 4 special limits. The first one, as x approaches infinity, of c over x to the n. That's supposed to say x to the n. Remember that if you plug in a number to x, like infinity to some power of n, if you have some number over infinity, what's happening if you have some number over infinity?
It's a smaller infinity.
The infinity on the bottom is making the number super small, like for example 1 over a million or 1 over a billion, you know? It's making the number super small, so it's going to 0. Okay? For the next one, the limit as x approaches infinity of this one. This is maybe a rule we haven't learned of yet. We haven't actually gotten to the section of the books where we talk about natural logs and exponential functions yet. So this probably isn't one that you guys know of yet, but we'll get there. You do know this one. We learned about that when we were first learning about limits. The limit as a approaches 0 of sine of a over a is 1. You guys remember learning about that at the very, very beginning of the year? That one was a long time ago, but we did. And then number 4, you also know. The limit as a approaches 0 of cosine of a minus 1 over a equals 0. We learned those 2, and those were ones you just had to memorize from a long, long time ago. It was probably one of the first days of limits that we wrote that in our notes. Yeah, reaching back far. All right, so let's go through a couple of these a little bit faster. We're almost done, so we won't too much longer here. But a lot of these ones we can actually just talk about because they're pretty simple to go through. So for example, what happens to this one as it goes to infinity? This term. What happens to that middle term as it goes to infinity? 4 over infinity is 0. What about this one? 0. So what's the limit of this? 3. Perfect. All right. What happens to the limit of this one as it goes to infinity? 0. What about this one? It goes to infinity. Good. How do you know that goes to infinity?
Because it goes back to the top.
Good. The x to the negative 2 goes back up to the top. So 4 times infinity squared is infinity. So this is 0 plus infinity, which is just infinity. So this limit actually does not exist. All right, what about this one?
3. No, it's not.
Remember this one? We did a couple examples like this a long, long time ago. Do you remember the trick? You have to like add in a 3 and then take out a 1/3 kind of thing or whatever. Actually, okay, I lied. It is 3, but not because, well, unless you remember back to then, not because of this 3. So it's not like you can just pull out that 3. I think a lot of you guys just thought it was 3 because you can pull out that 3. It looks like this. You have to multiply by 3 over 3.
Oh, yeah.
So this would be sine of 3x over 3x times 3. And this, the limit is that goes to 0, is equal to 1. So it's 3 times 1, which is 3. So you're right that it is 3, but I guess they'll never know what your thinking is on the AP test. Just be careful because they might try to confuse you or something. So that's the reason it equals 3, not because there's a 3 you can take out of the sign.
So would it be there's like a different, like, 2x on the bottom or something?
Yeah, maybe. And then it would be 3 over 2. Yeah. Which people probably still could figure out, but I just don't want, I don't know. It's one of those questions where it's like, when you think about it the wrong way, you still get the right answer. Which sucks, because it's bad to think about math the wrong way. All right. We're going to skip that one because that's the one that we haven't really talked about yet. I think you could do all of these. So why don't you guys go ahead and try all of these ones. You see I'm pissed?
Yes, I'm pissed.
Why?
Because senior power vote is not having practice because of the wind. Oh my god. So
It's pretty windy out there.
But they're still
Yeah,
practicing?
we're still practicing. And then, but also we have our banquet later, and they're just lazy. They don't want to like get dressed and stuff all rushed. So yeah,
That sucks.
we're dedicated.
Juniors. 1-5 seniors. No, we're not losing this year. Don't say that,
Did you guys lose last year?
Yes, we
Yes,
lost.
they
We lost
got
really bad
embarrassed.
too. Shut up. I don't want to hear you.
You got hurt at the exact same time.
Oh yeah.
So
Cindy,
just like
yeah.
they're
Both
just
of those.
leaving.
Cindy busted her lip and Tiffany hit her nose.
Well then.
Oh yeah, I remember those pictures. Oh, I'm gonna go home and get ready for the banquet. That's look nice.
Number 1 to start off with. What's the limit as x approaches infinity for number 1? Good, it's infinity. It does not exist. It gets confusing sometimes because infinity squared minus infinity doesn't really make sense. But if you have, if you think of it like its function, it's looking for a horizontal asymptote. But if you think of that, that's a parabola facing up, right? So obviously the limit as it's going to infinity is going to positive infinity. So there's nothing that it can equal. For this one, any ideas on this one? This is kind of like the rule that says cosine ax minus 1 over a. The limit as that goes to 0. So it's going to be like this. We're going to multiply this by 7 over 7. But we're going to keep that 7 out on the top. So it's 7 times 1 minus cosine 7x over 7x. This piece is really close to that rule. It's just the negative version of it. So if you pull out a negative from the top, you get negative 7 times cosine 7x minus 1 over 7x. Yeah. Which is just negative 7 times 0. Because remember the limit of that second piece is 0. So that's just 0.
Wouldn't you just figured out that you could use that rule? You don't even have to do any of that. You just know that it would be 0.
Pretty much, yeah. What about for the bottom one? For the third one, I mean. What can you factor out of the top? Factor out of 3, so you get cosine x squared minus 1, which factors to cosine x plus 1 times cosine x minus 1. Oh, actually, I think that's the wrong thing. Hold on. Small little eraser.
Is it x squared?
Mm-hmm.
Yeah. No, it's cosine x squared. That makes more sense. That's 3 times cosine x squared minus 1. There we go. Over 9 times x squared. So that's cosine of a minus 1 over a. The limit as that goes to a 0 is what? 0. Good. So this is equal to 1/3 times 0. The only reason I could think, like, on the AP test that they could trick you like that and have you actually make you know the rules is if they actually write out the steps and say, like, which of these is the correct step. Or, like, which of these is the correct way of doing it. Or, like, where is there an error in this step or something. Yeah, like, that's the only way I could think of them actually making you know these rules without just being able to figure it out pretty easily. So, yeah. And then what about the last one? Good. The x squared goes to the bottom, so that would be x to the 5th power on the bottom. The limit as that goes to infinity is just 0. All right, this next section is our last section. We get to go back to calculators. So we're so close to being done. So you can evaluate a limit with a calculator. So pretty much a limit is a height or a y value toward which a function is heading at a certain x value. So for example, the limit as x goes to 2 equals 4. 4 is the y value, 2 is the x value. Using that image of it in your mind with a graphing calculator will help you to simplify the process of finding what the limits are. So most of the times what the function will look really weird, but as soon as you enter it in your calculator, you can use your calculator to pretty easily figure out what the answer would be. So the easy questions will appear on the non-calculator portion, and the more difficult questions will appear on the calculator question. So keep that in mind as you go. So for example, something like this. This gives you something weird limit. Notice that when you plug in 9 on the top, you get 9 minus 3 is the square root of 6. When you plug in 9 on the bottom, you get 0. So this one is not the indeterminate form, so it's not like you can use L'Hopital's rule or anything like that. So actually, I would just put this in a calculator. So put that in your calculator. The square root of x minus 3 divided by 9 minus x. And you might want to change your window back to a good viewing window. Alright, did you guys graph yours? And did you get a good viewing window where you could see the graph on there? Here's the window I used. I used from 0 to 20 and from negative 10 to 10 for y. And that gave me this graph. Did you get it now? Try going back. Does your function look like this? The square root of x minus 3 divided by 9 minus x? Are you sure you used negatives and not minuses? You're welcome. So if you push trace and you go to 9, because it's the limit as x is approaching 9, obviously you won't get anything, because it doesn't exist at 9. But it's really easy to use your calculator and just be like, oh, if it doesn't exist at 9, what does it equal when it gets really close to 9? Let's see, 9.00000001. How about negative 2.45? Yeah. Sounds good to me. That was easy. So they'll put stuff like this on a calculator portion just because it'll be difficult to figure out. Say it again? Yeah, it just changed it back to 9. Yeah, it's really, really close to 9. You can also use the table. So like if you go to table set and set the independent to ask and the dependent to auto.
It's not like 2 point anything. It just goes 2, 4, 4, 9, 4, 8, 9, 7.
Oh, that's weird.
So, yeah.
Huh. Maybe try the table. If you do the table and you go 9.000001, it'll give you that 2.4 or something. I like the graph better because this one will give you e to the 7th, so it'll cut off a lot of the decimal places. The graph won't do that, which is nice. So I would stick with the graph if I were you guys. But yeah, 8.9999999. That'll give you the same thing. Oh, hey, my decimal place disappeared too. Look at that. That's a huge number.
It goes to 0.5. Yeah, that's what I got.
But look, that's not what it equals.
Yeah.
9.1111111111.
Yep, no, mine doesn't even have a decimal. What is this?
Or 9.000001.
Where did my decimal go?
Oh, that is weird. You know what? I lied. Did mine have a decimal place to start with?
The first time you
Yeah, it
did.
did.
That's weird. Because anyway, this is 9 right here, right? So it's actually going down to negative infinity over here, and it's going up to positive infinity on this side. So it makes sense not to have a decimal place. I'm not sure why mine had a decimal place the first time. That's weird. Anyways, not supposed to have a decimal place. It's going to negative infinity from the left, and it's going to positive infinity, or vice versa. Negative infinity from the right, and positive infinity from the left. Therefore, the limit does not exist. And it's really easy to tell that from a graphing calculator. Sorry, that was so confusing an explanation.
If you put enough zeros, it gives you a negative number.
What does? 9.000001?
Yeah, and you keep putting more zeros.
It has a negative number here.
Or, I mean, a decimal.
What kind of decimal?
Oh, never mind. Oh, it's a decimal because
3x squared minus 7 over 4 plus 2x plus 5x squared. Alright, my graph looks something like this. Too close. So they want to know the limit as it's going to infinity this time. What does the limit at infinity mean? A horizontal asymptote. So I see one horizontal asymptote right here. So how would you guys figure out what that would equal, that horizontal asymptote?
trace it.
I would either trace it or just scroll over there. But yeah, I would put in like some huge, well, let's see. I don't know if this will do this. Yeah, it won't work unless it's in your domain. If you actually like move your window out from like negative 1,000 to 1,000, it's going to give you a really crazy picture. I mean, you won't be able to see anything, but I don't really care what I'm looking at. If you trace that, if you trace it and type in x equals 1,000, just because I want to know what it's going to at infinity. Now, 1,000 is not very big, but it's probably following the asymptote pretty close by the time it gets to 1,000. So to 0.6. So what is 0.6 as a fraction? 3/5. So that's how you could figure out or prove that it's going to 3/5 is by just going out further and further using the trace feature of the calculator. So I would probably do that. It doesn't take too much time, and you can figure out that the further and further out you go, this number is just going to keep getting closer and closer to 0.6. If you didn't trust yourself the first time, go out to like 10,000 and try it again, and notice that it just gets super, super close to that number. I don't think that they could. This isn't so much of a test question. This is more of like I would think they would leave off the 3/5 part and then just say what's the limit of this function, and you would have to show that it's 3/5 or prove that it's 3/5.
How do you prove or explain?
The last one.
Yeah, like, well, using your calculator, how do you say?
I was just telling Miriam that I don't think that they would actually ask you to prove that on the AP test using a calculator because I would think that they would leave off the part about the 3/5 and then just say, what does this limit equal? And like you can use your calculator on it or something. That's what I would think. I don't think they would make you actually go through the whole process. Actually, well, I don't know, because it's super easy. You don't even need a calculator for it. How would you prove that on a calculator? I don't think this is a good AP test question because it's really hard to show them what you're doing on your calculator. I think it's just more for you to use your calculator to see it. Normally they wouldn't be this simple functions, but yeah, I don't think they would do that to you. All right, given p of x equals that, find the value of b that ensures p is non-removably discontinuous only once on negative infinity to infinity. Do you guys know what that implies? I have seen a question like that actually on the AP test before, so I do want to go over that one. Ignore 1, we're looking at number 2. Yeah, so let's do that together. So let's look at number 2. So what is the bottom factor to? Right? 2x minus 3x plus 5. You guys good with that piece? So it says find the value of b that ensures that p is non-removably discontinuous only once on negative infinity to infinity. So what are the possibilities for non-removable discontinuities? A jump, which we won't have here because remember jumps only come when we have piecewise functions, or a vertical asymptote. So that means that only one of these is allowed to be a vertical asymptote, the other one has to be a whole. So we need to figure out what value of b up here could help us fit into one of these. Which one do you guys think we're going to help fit into? X plus 5. We can't make that up there. We can't do anything with that too. So we shouldn't use the first one. We have to make one of these factors an x plus 5. So b is what? So what would b be? b be? 20, is that what you said? What would make so something there plus this would make that equal something. So x squared plus 4x plus b. Yes. So minus 1 would make that equal 4. Awesome. Good. And then, yeah, b would equal negative 5. Did that make sense a little bit to those of you guys who were following along? Not really? Where'd we get b? Okay, so let me erase what we just did really quick. So essentially, do you understand how we factor the bottom first? Okay, then do you understand what it means to have a removable discontinuity? What is a removable discontinuity? What would a removable discontinuity look like on the graph? There's 3 types of discontinuities: unbounded, jumps, and holes. Which of those is a removable one? The whole is removable, right? When we're looking at an equation in factored form like this, how do you know if it is a whole? What do you mean you can take it out? You're right, but I want you to be more specific on what you mean by that.
Like the x plus 5,
Good. The fact that you have the same factor on top and bottom, you can take them out or you can cancel them on top and bottom. That's what proves that there's a whole here. So what I'm trying to do is it says that there's a non-removable discontinuity only once. So we're going to say that this is our non-removable discontinuity, that there's a vertical asymptote there, all right? Because we think we can make this one cancel out with something on the top. So automatically I have to put that same factor on the top so that I know I can cancel those two out. So that automatically is my whole. That's my removable discontinuity, which means I need to figure out what this missing piece of the puzzle is so that when I multiply them back together again, they fit into this form of a binomial, or a trinomial actually. So I was trying to figure out, or we were trying to figure out, I should say, what number we were plugging in here that would make this 4 happen. And that's how we figured out x minus 1, because that's the only thing you can plug in there that would bring that 5 back to a 4. Does that make sense? Yeah. So that's how we got that was negative 1. And then to figure out what b is, the b term would just be the last term. So negative 1 times 5 gives me negative 5. So that's how we got b equals negative 5. You're welcome. And then the last one, what conditions must be met if f of x is continuous at x equals c? What conditions must be met if f of x is continuous at x equals c? Let's skip that one for right now. That one's just asking, well, it's a limit, what do you notice the limit's going to? Negative infinity. Actually, it should be really easy then. When you multiply the top, what's the leading degree, or the highest degree, I should say? S squared. And what's the leading degree on the bottom? S cubed. So my horizontal asymptote is at 0. Good. So this one's just y equals 0, or the limit equals 0. Yeah, because it's a horizontal asymptote goes in both directions, so it follows it to the positive and the negative side. Yeah. Don't worry about number 5 right now. That's above our pay grade for the last 10 minutes of our function. What 3 functions behaviors prevent a limit from existing? We already talked about that. We've talked about this before. Oops. There we go. What about 8? I think we can do 8 really quick.
Still 0?
Say it again.
0? Is it negative?
Yeah, I just squared to the top. I mean, sorry, it's 0. So it'd be like minus 4x to the negative 2. Yeah. And then you bring it to the bottom. So it would be, let's call it 4x to the negative. What? Yeah. No, I get what she's talking.
Here's what I would do just to make it simpler in my mind, because I think some of you guys are on the right track, but here's what I would do. I want to, because I have infinity minus 0 over 2 minus infinity, that's probably going to be a little confusing. So I'm going to multiply the top and bottom by 1 over x. So 2x times 1 over x is what? 2. And then negative 4 over x squared times 1 over x is negative 4 over x cubed. 1 over x times 2 is 2 over x. And then 3x times 1 over x is just 3. So the limit as it goes to infinity, this piece is going to go to 0. This piece is going to go to 0. And I'm left with 2 over negative 3. So negative 2/3. So this is actually a leading coefficient test. The leading coefficient is 1. The leading coefficient is 1. 2 divided by negative 3.
So the x would be like negative? It would be x and negative?
Yeah. Good. All right, I think, let me see, make sure. I think this is the last one that I want to look at today, at least. 10's kind of a trick question, by the way. Can anybody tell me why it's a trick question?
The limit has to approach 0?
Yeah, the little trick, remember the little trick we learned about sine x over x equaling 1? That only works if the limit's approaching 0. So in this case, the limit as x approaches 2 of this is just sine of 2 over 2. So you just directly substitute it into the equation and get sine of 2 over 2. So I would think that would probably confuse some people on that one. All right, this is the last one I want to look at. And then we're going to be done, and I'm going to let you guys rest your brains. Most of these should go by pretty quick, and it's kind of a good wrap-up, because none of you guys were here when we started at the beginning, but this is what we started with at the very beginning. So if d of x is defined by the graph below, answer the following questions. We'll talk about them together. You don't have to write them down. The first one, the limit as x approaches 0. We'll go around the room round robin, so you guys can each have a turn. So who wants to start off on this one? What is the limit as x approaches 0? All right, Judith, you're frozen. She gets 0. That means that's your question to answer. She got 0 because, look here, as x approaches 0, the graph is going towards 0, right? So there you go. It's 0. For the second one, the limit as x approaches, what the heck is that? I think that must be a typo. It's like an N with a tilde on top. I don't think that was supposed to be there. I don't even know what that is, so we're just going to skip that. I don't think that's just a typo in their book, because that's nothing you need to know. What about D? The limit as x approaches 2. Sierra, you're frozen.
Well, there's a removal, but it doesn't matter, it could be at
Remember, limits don't have to be continuous. Limit is like, what is it going to? The limit does not say it has to equal that value, it's just what is it going to. So if you look from both sides as it's going to 2, or as it's getting closer to x equals 2, it's actually going to y equals 2. Even though it equals this point down here, it doesn't matter. It's what it's going to, not what it actually equals. So that one's going to 2. Good. So we have 2 people frozen. The limit as x approaches 4 from the positive side, what's that? From the positive side is going close, not 4.
Oh, 0.
I think you just counted wrong, but you were closer the first time.
Oh,
3. Good. This is the 3. The limit from the, oh my gosh, what am I doing? There we go. The limit as it goes from the right-hand side as it gets closer to 4 is going to 3. F, list all x values where D is discontinuous. Where is D discontinuous? I hear -2, that's correct. Say it again.
3.
Positive 3?
Yeah.
Not quite.
2. Just kidding, 2.
It's continuous at 2. Oh wait, discontinuous. Yeah, you're right. Discontinuous at 2.
4.
At 4. There's one more place. -3. Good. So it's discontinuous here because it's unbounded, here because there's a jump, here because there's a hole, here because there's a jump. So there's 4 places where it's discontinuous. Which of these does the limit exist at? There's only one of these that the limit exists at.
2.
The limit exists here because that's a removable discontinuity. If it's a removable discontinuity, the limit still exists because from both sides it's still going to the same number even though it doesn't equal the number at that place. Which of your answers to part F represents removable discontinuities? We just talked about that. H, what values of B make the following statement true? So there's actually only one value of B that makes that statement true.
Yeah, we're still in.
Good, -3, because it goes to positive infinity on both sides. Good. So this is the only place at -3 that makes it go to positive infinity. All right.